Welcome to part 2 of solving least squares equations. This is called ax equals b and least squares. So part 1 was just a simple example of fitting a straight line or a polynomial to a number of points. It was just to whet your appetite. So let's have some nomenclature and definitions to start with. So here we've got a matrix. It's got m rows and n columns. We've got an n by 1 column vector and we've got an m by 1 column vector, and we write it like this: ax equals b. And the question is, if we're given a, given the values for a and given the values for b, what is the solution for x to satisfy the equation above? And if no solution exists, then what is the least squares solution? So a warning before we actually start: matrices behave very differently from scalars. So if I asked you what's the value for x, 3x equals 6, you'd say x equals 2. And if I multiply both sides by some constant, in this case 5, I get 15x equals 30, and x is still equal to 2. Multiplying both sides of an equation by the same amount doesn't change the solution for x. Now take ax equals b here. Take my word for it, there's no solution for x in that equation, or that set of 3 equations. Now what if I multiply both sides by something? I'm going to multiply them by A transpose. So if I multiply both sides of the equations by A transpose, remember what a transpose is. It's where the first column becomes the first row and the second column becomes the second row. Multiply those through and then solve, and you get this answer. So does that mean that that's the solution for x in ax equals b? The answer is that's not the solution for x, because we know there's no solution. So in this case, where you had no solution, multiplying both sides by the same matrix gives you a solution. So be careful you don't do that. If there was a solution and you multiplied both sides by the same matrix, that wouldn't be a problem. But in the case where there's no solution, you can create one, a false one. So that's a very classic undergraduate mistake. So we can have 3 different types of matrices. We can have what's called a square matrix, which is pretty obvious. We can have a fat matrix, which has more columns than rows. And we can have a thin matrix, which has more rows than columns. And I'll refer to these by these names: square, fat, or tall. So if you take these 2 equations, it's simple to find the solution, which is this here. And we can write these in the form of ax equals b, just like that. So when we say solve ax equals b, we're trying to find the value for x, the column vector x, that will satisfy ax equals b. So there you have it, ax equals b, and we can take the inverse if the inverse exists, and we get that. So this is old school level stuff. Now, we've assumed that a is square and invertible, and that's not always true, as we're going to see. So there is no column vector that satisfies this. You can't make the left-hand side equal to the right-hand side, so what do we do now? So the least squares solution is this. Now, I'll show you how to get this, but what do I mean by least squares solution? So plug that value in there and see what we get. So when you plug that in, the right-hand side becomes this. And it's approximately equal to b, which there's b up there. So you can see what I mean by least squares roughly. It's making the right-hand side approximately equal to the value b, but not exactly. So how do we get this? So when we say solve ax equals b, what we really mean is find the column vector x that makes ax equals b exactly or approximately equal to b in some optimum or least squares way, and that will be explained. Now there are 3 possibilities for ax equals b. You can either have one unique solution, and that means it's a consistent set of equations. If the left-hand side equals the right-hand side, it's consistent. You can have a consistent set of equations, but there are an infinity of solutions. So there's either one unique solution or infinity. The set of equations can be inconsistent. That is, there's no solution for x. So the left-hand side will never be equal to the right-hand side. That's inconsistent. So we've 2 new terms: consistent or inconsistent. So here's an example of one solution, 2 equations and 2 unknowns. Here's an example where we have 2 equations and 3 unknowns, and there's an infinity of solutions. It's consistent, and it's what's called underdetermined. That is, there are more unknowns than equations. Up here we say it's exactly determined when you have the same number of unknowns as equations. I should just point out that what we've got here for 1x1 plus 3x2 plus 5x3 equals -7, that defines a plane. Not necessarily that plane, but it defines a plane. And what we've got here is two planes and they're intersecting. That gives you a line. And so what you've got is a whole series of solutions lying on that particular line. And overdetermined case where you have got more equations than unknowns, and this is inconsistent, so there's no solution. So there's some visualizations of those three cases. Now we have got 6 possibilities, and those 6 possibilities come from the fact that A can be square, fat or tall, and that this set of equations can be either consistent or inconsistent. So 3 times 2 gives you 6. Now if it's inconsistent, then we need a least squares solution. So let's have a look at that least squares solution to ax equals b. So remember that no column vector satisfies this set of equations. So how do we find the least squares solution? So we're going to have a temporary change in nomenclature, just going to go to y and x rather than x1 and x2. So there's 3 equations, and there is no solution for x and y that will satisfy all 3. So what we do is we add an error to each one equation. So watch what happens to equation A when I add an error to it. It moves in some direction like that. I take equation B and I do exactly the same thing. I add an error to it and it moves. And then I take the third equation and I add an error to that, so it's going to cut exactly there. And I get this. Now the thing is, there's an infinite number of error terms that I could add such that all 3 lines will land in the same point, i.e. they'll be consistent. And the question is, which one is the best? So many possibilities. There's one possibility. There's another possibility. And the question is, we want to do it in such a way that the sum of the error terms is minimized. Why do we want to choose the sum of the error terms to be minimized? Because if we do that, the red point is going to land somewhere in the middle here, which intuitively seems to be correct. I.e., if you want to get a rough approximation to where those 3 lines intersect, inverted commas, then it's somewhere in the middle here. And in that case, you will sort of minimize the sum of the squares of the errors. So that's the intuitive explanation as to why we choose a least squares solution. Okay, so the least squares solution is 4, 5 in this particular case. And the way we do it, as before, is we just write it like this and we differentiate. And we end up getting the solution 4, 5. And we get this error term here, which is the lowest energy error term that you can get in order to make the 3 equations consistent. So there's no other vector whose error energy is smaller than this one and also gives you a consistent set of equations. So if we return to our original nomenclature, and so what we've done here is simply to go back to x1 and x2 and to stack them into matrices and vector form, so we get this. And now what we want to do is, I've just changed the sign here. It was plus on this set of equations, but this is just for simplicity later on. We want to find the x that minimizes the square of the norm. And the square of the norm is just the sum of the E vector and all the terms in that squared. And we can do that by taking E transpose times E. So what we have is the least squares solution is equal to this, the argument min over x norm squared b minus ax, which is just equal to the norm squared of the error vector E. And what I mean by arg min, what it means is it's the argument that minimizes this. So it's the value of x, because x is the argument, that minimizes this norm squared. It's not the minimum itself that we have on the left hand side, but it's the argument that minimizes. So if we have a look at those cases again, here's where we've got one solution, and that will pick it up. Here's where we've got an infinity of solutions, and again this would pick it up. Here's where we've got no solution, and that's the least squares solution, that would pick it up. And here we've got an infinity of solutions. Where there is a solution, this will go to 0. Where there isn't a solution, this will be at a minimum. Clearly this cannot go smaller than 0. So in order to solve that problem, you just need to know some very basic matrix calculus. So if you expand that out like this and then differentiate with respect to x, you end up getting the normal equations. So these are quite famous, remember this. And any solution for this, no matter what the case is, it will always fit the normal equations. So we have to look now at how we solve the normal equations. So when this term is invertible, we can just write down the least squares solution is given as that. And it's there, it is there. So if I put those values in, you can see how I get that. Now what happens when A transpose A is not invertible? What do we do? So before that we need to make a short digression and look at the idea about matrix rank. So what's the rank of a matrix? The rank of a matrix, and there are many definitions, one definition is, and they're all equivalent, is that the rank of a matrix is the maximum number of its linearly independent column vectors or row vectors, it doesn't matter which. And what's the definition of linear independence? It basically says that if you take p vectors and you weight them by alpha 1, alpha 2 and alpha p, the only way that you can make that weighted sum equal to 0 is if it satisfies all of these coefficients equal to 0. If that's the only way you can make it equal to 0, then these vectors are linearly independent. So let's take an example. What we've got here are 3 columns of a matrix, and we can show that we can add them like this to get 0. So those 3 columns are not linearly independent. So the number of linearly independent columns must be less than 3. So the rank must be 2 or 1. It's easy to see that only 2 columns are linearly dependent, and so we can say the rank is 2. And if the rank is less than or equal to the minimum dimension of A, so in this case the dimension is 3 by 3, the minimum dimension is 3, we say that A is rank deficient or not full rank. It doesn't have to be a square matrix, it could be fat or it could be tall. But we will see that the rank is always less than or equal to the minimum dimension. But we'll use this word rank deficient or not full rank. And other equivalent definitions of rank include the column space dimension, which we're going to look at, or the number of non-zero singular values from singular value decomposition, which will come later. So the rank of a matrix is the dimension. It can be defined as the dimension of the column space of A, where dimension refers to the minimum number of basis vectors needed to span that space. It's much easier understood if I just do a figure. So here we have a matrix A. It's got 3 column vectors. And we know the rank of A is equal to 2. How do we know that? Because the third column vector is made up of twice the first plus twice the second. Okay, so we know that the rank must be less than or equal to 3. It's easy to prove that it's 2 after that. Now if I draw A1, A2 and A3, we find they lie like this. These are 3 vectors. They're all 3-dimensional vectors, or 3 by 1 vectors. Okay, don't mix up the 3 by 1-ness of the size of the vectors with the space they span. They span a 2D space. Now, what's the minimum number of basis vectors that you need to span a 2D space? You only need 2 basis vectors. You need less, like having 2 axes, and that can take you to any place in that space. So that dimension of 2 is the rank, and the rank of A is equal to 2. Okay, let's have a look at this one. In this case, the rank of A is equal to 3. And if I draw those 3 vectors, you can see that with those 3 vectors, and you add them together or weight them together, you can go to any point in a 3-dimensional space. So the space of the column span of A has got dimension 3, and you need a minimum of 3 basis vectors to find any point in a 3-dimensional space, so the rank is equal to 3. So let's have another important definition, rank and consistency. We can use rank to determine consistency. So remember that AX equals B is consistent, that at least one solution exists. We can either have one solution or infinity of solutions if it's consistent. So if you look here, what we've got here is one column vector, another column vector, and we know that B must be equal to, if it's consistent, A1 times X1 and A2 times X2. So if it's consistent, B must lie in the same space as A1 and A2, because you've got two vectors here. They lie in a two-dimensional space. And so B must lie in that same two-dimensional space. What I mean by spanning it is that you can choose values for X1 and X2 such that you will end up able to get B. So choosing the correct value for X1 and X2, you'll find B. It's just addition of vectors. Okay, so if you take the rank, if you take A and you add an extra column, that is B, so now you've got a 3 by 3 matrix. Its rank must be no different than the original rank of A. Why is that? Because B is not linearly independent of A1 and A2. So adding in B will not increase the rank. It'll keep it exactly the same, since they must lie in the same space to be consistent. So that's a necessary and sufficient condition for consistency. Okay, here's another example where they lie in a space of dimension 1. Okay, it's just still consistent, but they lie in a space of dimension 1. And it's the same result here. Adding in the vector B does not change the rank of A. Okay, here's a situation where AX equals B is inconsistent. So that means that we cannot say B is equal to X1 times A1 plus X2 times A2. So what does that mean in terms of looking at the vectors in space? So what we'll have here is A1 and A2. They're two three-dimensional vectors, and they will lie on a two-dimensional space. Don't get confused with the dimension of the space and the dimension of the vectors. These are 3 by 1 vectors, but they're lying in a two-dimensional space. So they can span, or they can access any point in that two-dimensional space by choosing the correct value for X1 and X2. There's no way that they can ever give you B, because B doesn't lie in that same space. So that means that if you take A and you add an extra column in, then the rank will be different, because B is linearly independent of these two. So the rank will now be 1 larger than A. So this is a necessary and sufficient condition for inconsistency if the rank of the augmented matrix AB is not equal to the rank of A. So here's some general results for matrix rank, just to be complete. This is what I referred to earlier, that the rank is always less than or equal to the minimum dimension of the matrix. M is the number of rows and N is the number of columns. Okay, let's return now to the normal equations after we have defined rank. And the question we're going to ask ourselves is, that we were asking before, when is A transpose A not invertible? So when A transpose A is not full rank or rank deficient, it's not invertible. And this can occur in two ways. Now note that the rank of A transpose A is equal to the rank of A. And using this result, we can show these two ways. So if A is not full rank, and it doesn't matter whether it's fat, square or thin, then this will not be invertible. Now how do we prove that? Well, you use this result and you use the fact that the rank of any matrix is less than or equal to its minimum dimension. And if you use those two results, you can show in all these three cases, whether it's fat, square or thin, as long as A is not full rank, this will not be full rank, and so it will not be invertible. And in that case, you must use the pseudo-inverse to solve for the minimum norm solution for X. There's no other explicit solution. The second way is if A is fat and full rank. So we said if A is not full rank and fat, then it's not invertible, A transpose A. But if A is fat and full rank, it's also not invertible, but we can have an explicit expression here. So that's the difference. You still use the pseudo-inverse, but you have now got an explicit expression. So a summary of those expressions. When A is full rank, you can write the least squares solution in 3 different ways. And for any other case, you're going to have to use the pseudo-inverse. By the way, just to see how it's done, let's have a look at how we derive this last equation. So now let's go back to the minimum norm solution to the normal equations. That's where we were originally at before we made the digression to look at rank. So we want to see how we derive this expression here. So the problem that we've got when we A transpose times A is not invertible is we're having an infinity of solutions. It's underdetermined. We have got more unknowns than equations. So we have 2 equations and 3 unknowns, and we've got an infinity of solutions and also an infinity of least squares solutions. So to find the minimum norm solution, we say minimize the norm squared of the vector x, which is this here, subject to ax equals b. So this will lie on this line, and we want to find the smallest norm, the smallest length. And the way we do it is to form the Lagrangian like this. So we say we want to minimize this plus this times ax minus b, and this is a row vector. Lambda to the transpose is a row vector. So we differentiate with respect to x, and we differentiate with respect to the Lagrangian. And then we have 2 equations and 2 unknowns, lambda and x. We substitute in for lambda, and we get the value x, which is this. So that's how we do it. Form the Lagrangian, and then do this substitution. Okay, so that's how we formed that solution, how we found that solution for the minimum norm to ax equals b. So one way of picking up every single possibility is to use what's called the pseudo-inverse, and we're going to come on to that in a bit more detail. Here's an example where we've got 0 solutions to ax equals b, but infinity of solutions to the least squares problem, and we'll pick that up with this. There's no explicit expression in terms of a and b. In the case here where we've got an infinity of solutions to ax equals b, as we've seen, we could either use the pseudo-inverse or we have this explicit expression here. So in this particular case here, we can use this expression. Now, one of the advantages of using the pseudo-inverse, and we calculate that by singular value decomposition rather than using this expression, is because of better numerical accuracy. There's other reasons as well. But let's say we are trying to invert this. This is a square matrix. And although it's full rank, we're assuming it's full rank, the problem is it could be very close to being rank deficient. And what I mean by close is the ratio of the maximum eigenvalue to the minimum eigenvalue. And if the minimum eigenvalue is very small, you get a very large number. And when you try to invert a very large matrix that's close to being rank deficient, when you're doing that on a computer because of finite word length issues, you can get inaccuracies, but you don't get the same inaccuracies using the pseudo-inverse. So that when I say the pseudo-inverse, doing that by singular value decomposition. So let's have a look. If you take any matrix, you can break it down into 3 matrices here. And these are called the singular vectors, and these are called the singular values. There's an analogy between these singular vectors, the singular values, and eigendecomposition, but I haven't got time to go into that. Now these have got certain properties. You can look at these yourself if you wish, but if you want to find the pseudo-inverse, then what you do is just a slight rearrangement and you get this expression here. You might question how you can write the pseudo-inverse in terms of the pseudo-inverse of this, and the reason for that is because this is a sort of diagonal matrix. It's not square, but because there's diagonal terms, you can easily find this, which is just by inverting each term on the diagonal, and so you get this expression. R is the rank of A. So then you can write down that the solution is given as this. And again, to summarize, in certain cases this simplifies to these expressions, But if these are large and close to non-full, close to being rank deficient, then we prefer to use the pseudo-inverse. So let's take an example. Let's take this matrix A and this vector B, and let's try and derive the expression for the minimum norm solution. So we take the singular value decomposition. You can use that and do that in MATLAB. There's what I mean by a sort of diagonal matrix, okay? Now, when you take the pseudo-inverse of that capital sigma, all you do is invert each element. So it's quite simple. And then you get the solution, which gives you this. If you were to do it explicitly using this, you get exactly the same answer. But don't forget, for the reasons I've said, we prefer to use the pseudo-inverse. Let's take another example. So here we've got an example of where we've got no solution, an infinity of least square solutions. There's no explicit expression here. So what's the minimum norm solution? Again, I do the singular value decomposition, find the pseudo-inverse, and the minimum norm is 1.8.6. Okay, that's finished part 2. We're coming on to part 3 now, which is visualizing the problem. And what I want to do here, instead of going through maths really, I just want to try and show you visual representations of the various issues that can occur when you're dealing with fat or square or thin matrices, which give you consistent AX equals B or non-consistent, and when you have rank deficiency. I think you get a better understanding by looking at diagrams. So I'll see you in part 3.